Beishuizen from so my name is Nijso Beishuizen from Bosch Thermal Technology in Deventer, as well as TU Eindhoven. And for the next, let's say 40 minutes or so, I will tell you a little bit about combustion modeling and the design optimization for combustion applications with a focus on hydrogen. And I have selected a couple of topics for you. So I will start with a brief introduction about hydrogen in the built environment and tell a little bit about the differences between hydrogen and natural gas. And I will then briefly discuss some models for combustion and hydrogen. And then I will close with a short, let's say, introduction to a joint design optimization and show you some nice results. So to start with the introduction, so I work for Bosch. Bosch is a very large company with over 400,000 employees, making many products ranging from washing machines and gas boilers to components for the automotive industry. And at our location in Deventer, we make domestic gas-fired wall-mounted boilers. So these boilers are used to provide heat for warm water, warm tap water and shower water, and for heating your house. An example of such a boiler is shown here. I'll briefly explain how this works. So this is what I do for most of the time. Working on the development of these boilers. So let's see if I also have a mouse somewhere. Yeah, the laser pointer. Yeah. So basically, what we have is we have a fan that sucks in air from the environment into the system through the suction pipe. The air then flows through a venturi, which creates an under pressure that opens a gas valve, allowing natural gas or hydrogen fuel gas to enter the appliance. The fuel and air are then completely mixed before the mixture flows through the burner. You see a cross section here. The yellow part is the burner. The flames are stabilized on the burner. The hot combustion products are then flowing through the heat exchanger downstream of the burner, and water channels run through the heat exchanger, and the water extracts the heat, which can then be used for showering or for heating your house. Now, a possible future decarbonization scenario is one where domestic natural gas, currently used for household heating and cooking, is replaced by hydrogen. Energy is generated offshore by wind turbine parks. The energy can be converted into hydrogen using an electrolyzer, and the hydrogen can be stored either onshore or offshore. And the hydrogen can then be transported through the existing gas lines to homes and industry. So this is a potential future. Now, why is hydrogen as an energy carrier attractive? Why not simply create the electricity and transport that to industry and houses and use, for instance, heat pumps to heat your house? Well, some studies have shown that a full direct electrification of heating is not feasible, or at least it will be very expensive, as this would require a significant increase in electric power generation, so peak power and grid capacity, just to cover the peak usage in wintertime. This would require massive investments. However, existing houses have gas lines that can be reused with less investments from the perspective of energy suppliers, as well as from the perspective of the homeowner, since many older houses also need major investments before a heat pump can be installed. So furthermore, 90% of all emissions from the built environment result from buildings older than 25 years. So tackling these houses and offering a low cost, or at least lower cost solution will have a large impact on the total CO2 emissions from this sector. And this infrastructure is already in place. The gas lines are there. Pilot tests are done on domestic gas lines. Regulations for domestic gas appliances are updated to take into account the future movement towards hydrogen blends and 100% hydrogen appliances. And if we look at all of Europe, hydrogen for heating can help 40% of European households to become independent of natural gas for household heating and to significantly reduce the CO2 footprints. Now, 3 main scenarios have been identified to introduce hydrogen for heating. In scenario A, called blending, hydrogen will be added to the existing gas grid. And over the course of time, the hydrogen concentration can be increased to what existing appliances can handle. And in scenario B, hydrogen islands will be created, where a part of the gas grid is upgraded to a close to 100% hydrogen net. Customers connected to a hydrogen island then need appliances that are suitable for 100% hydrogen fuel. And in scenario C, all appliances in the Netherlands will be made hydrogen ready, meaning that they can run on 100% hydrogen, but also on 100% methane. They are installed in a classical natural gas network, and when locally hydrogen islands are introduced, only a small modification is necessary to switch the end customer from natural gas to hydrogen. And of course, then the debate is about what does small mean. So at the moment, all these 3 scenarios are still on the table, which is why it is necessary to have appliances that can deal with these different scenarios, from mixtures of natural gas and hydrogen to 100% hydrogen boilers. And to assess what needs to be done, it is important, of course, first and foremost, to identify the differences between natural gas, so methane, and hydrogen. So what is actually the difference between hydrogen and methane? Now, one of the most important differences between hydrogen and methane is the energy content, or the heating value of the fuel. The volumetric energy content of methane is more than 3 times higher than hydrogen. However, the energy content per kilogram is almost 3 times higher for hydrogen when compared to methane. And this means that for a flame, if we keep the volume flow rate of the fuel the same, or equivalently, we keep the flow velocity the same, then a hydrogen flame will have a lower power than a methane flame. Now, on the other hand, hydrogen needs less oxygen compared to methane. Hydrogen needs only 1/4 of the oxygen for stoichiometric combustion. So if you also keep the equivalence ratio the same, the total volume flow rate actually does not change that much. So there is actually, in that sense, a small difference between methane and hydrogen. Now, one of the challenges of switching from natural gas to hydrogen lies in the fact that the flame temperature is much higher for hydrogen flames. So we see here that for an equivalence ratio of 0.8, which is a standard operating condition for boilers, the flame temperature of a hydrogen flame is almost 160 degrees higher compared to a methane flame. And when we look at the laminar flame speed of methane and hydrogen, we see that the laminar flame speed for hydrogen is more than 6 times higher than for a methane air flame at the operating condition. Now let's first talk a little bit about emissions. Now, the most important emissions for natural gas appliances are carbon monoxide, which is very poisonous, and nitrogen monoxide, which is a greenhouse gas, and it also reacts to nitric acid, which causes acid rain. So these emissions are definitely emissions that you want to avoid. Now here the process of the formation of these unwanted emissions is illustrated. And we start with a cylindrical burner here in the middle, in this axisymmetric geometry. And we can consider a small 2-dimensional axisymmetric section, which we see here. So here we have the symmetry line. Then the blue part is, let's say, inside the burner. Then we have the start of the flame region just above the burner surface. And then downstream, we have a cylindrical coil that is surrounding the entire burner. It is filled with flowing water and it extracts the heat. So we can identify different zones here. So we have a cold zone where the premixed fuel and air are transported to the burner surface, and the flames are stabilized on the burner surface. So A burner is merely a method to keep the flames at a fixed position. And in the flame zone, the temperature quickly increases and reaches the flame temperature. And this hot zone will remain at a constant temperature when no further heat losses occur. Then downstream, we have the heat exchanger. And in the heat exchanger, the hot combustion products are forced through narrow gaps between the water channels where the heat is extracted for hot water demand. And the combustion products can then cool down to the water temperature. The combustion process converts methane and oxygen, or hydrogen and oxygen, into water, and in the case of methane, also carbon dioxide. However, the carbon dioxide is produced in two steps. And first we have carbon monoxide, which is formed, and then the carbon monoxide continues to react to carbon dioxide. And the reverse reaction also occurs. And carbon dioxide reacts back to carbon monoxide. Now this process is basically shown here. This in the flame zone, all the carbon monoxide is produced. And after the flame zone, part of the carbon monoxide reacts to CO2 until an equilibrium situation occurs where CO and CO2 are produced and consumed in the same amount. And this equilibrium depends on the local temperature. Now, when the temperature decreases in the heat exchanger, a shift in the equilibrium occurs, lowering the CO. The temperature drops very fast in the heat exchanger. And quickly, the temperature is so low that all chemical reactions stop. Now, nitrogen oxide, on the other hand, is formed when nitrogen and air start to react in high temperature regions. Nitrogen oxide is formed in the reaction zone and keeps being produced as long as the temperature is high. And in the heat exchanger, there's still some NO that reacts to NO2, but also these reactions quickly stop. So if you would like to minimize CO or NO emissions, there are certain things that you can do depending on where you want to do it. So for instance, you can slowly cool the combustion products in the heat exchanger if you want to lower the CO, so this gradual cooling profile. However, this slow cooling has then an adverse effect on the NO concentration. So simultaneously optimizing CO and NO is a challenge. Another thing that you can do is lower the fuel to air ratio, the equivalence ratio, making the flame leaner. So this is usually expressed in terms of the equivalence ratio. Basically, if we lower the equivalence ratio, we add more oxygen, which cools, which lowers the flame temperature. Now, if our combustion processes can be approximated in the first instance as a one-dimensional problem, we can use one-dimensional detailed chemistry codes like Cantera, Chemkin, or Chem1D to analyze emissions. So in the previous figure, we saw that NO emissions linearly increase with distance from the burner, or equivalently linearly increases with the residence time in the hot zone. So we can therefore plot the NO emissions as a function of this residence time and the equivalence ratio. So in the left figure, we see the NO map for methane, and in the right figure, we see the NO map for hydrogen. So we can look up the NO for our operating conditions. So our operating conditions were equivalence ratio 0.8, and let's say our residence time of, let's say, a pocket of combustion products in the hot zone is 20 milliseconds. So our NO emissions are then 40 milligrams per kilowatt hour. So we can use such maps to make an estimate of the exhaust emissions of NO when the residence time is reduced or when the equivalence ratio is lowered. So we see that NO is much more sensitive to the equivalence ratio than to the residence time. If we want to lower NO to, for instance, 10 milligram per kilowatt hour, we have to lower the equivalence ratio to below 0.65. So for hydrogen, we see a similar picture, but because its flame temperature is higher, we have a higher NO concentration than for the methane flame, even when the residence time is reduced. So for a hydrogen flame, we can reduce the NO from 100 milligram per kilowatt hour down to 10 milligram per kilowatt hour by lowering the equivalence ratio to below around 0.55. Now, of course, this does mean that the total volume flow rate through the system increases. So this is maybe not a solution that is feasible. So there are other methods, of course, to lower NO emissions, for instance, fuel gas recirculation. But these kind of maps illustrate how 2D emission maps can be used in the first design iteration. So the higher flame temperatures can lead to higher NOx emissions. The higher flame speed of hydrogen can give rise to flashback. I will not go into the topic of flashback in this presentation. And if you want to know more about flashback, please watch the Combustion Institute presentation of Sikke Klein for a very nice introduction into this topic. So now I want to go into the modeling of combustion and hydrogen a little bit. So at chemistry in high school, we learned that a fuel like hydrogen reacts with oxygen, and this results in a combustion product, water. The reality is unfortunately much more complex because the molecular bonds need to be broken before they can form new molecules, leaving you with many combinations of carbon, hydrogen, oxygen, nitrogen atoms and molecules, because also nitrogen and carbon from the air participate in the reactions. So as an example, this hydrogen mechanism from the University of Galway has 44 species, 251 reactions. The number of species determine the number of transport equations, and the number of reactions determine the production and consumption source terms in these equations. So that means compared to just solving the Navier-Stokes equations, a huge increase in the number of transport equations that need to be solved in case of detailed chemistry solutions. So which equations do we need to solve when we have chemical reactions? So next to the Navier-Stokes equations, we need to solve a large number of transport equations. So they contain this source term that depend on the mass fractions of all the other species, the species I reacts with. And in this source term, Wi are the molecular weights and nu I are the stoichiometric coefficients in the reaction equation. K is the reaction rate given by the Arrhenius law. And this detailed chemistry formulation leads to a very large number of equations, but also to very stiff equations. So the source terms are very large. The species equations are coupled through the source terms. So last but not least, the exponential character of the source terms results in very thin regions where the source term is very large. So in the flame, in the flame, and to capture this accurately in numerical simulations, we need very small mesh sizes. The computational cost of these simulations is quite high, and one solution to this challenge, let's say, is tabulated chemistry. So what we do in tabulated chemistry is actually we perform detailed simulations in 1D only, and we map them as a function of progress variable, which we call C, which is a measure for the progress of combustion. And then 2D and 3D simulations, we can then solve together with the Navier-Stokes equations an equation for this progress variable and enthalpy, and properties like temperature, density, etc., chemical reaction rates are all stored and retrieved from the lookup table. So how well does this work? Well, it turns out that this approach works very well. Unfortunately, not for all kinds of species. So you guessed it, it does not work very well out of the box for CO and NO. So when the cooling is very strong, like in heat exchangers, tabulated CO and NO values are not very accurate. The reaction rates slow down, and the flamelet approximation for slow reactions is not accurate. And the solution is to solve then additional transport equations for these quantities and store and retrieve only the reaction source terms. So we can also split the source term that we need in the transport equation for the progress variable into a production term and the consumption term, because the consumption term is linearly dependent on the mass fraction of the species. So what we do is for the 1D simulations, we divide this term by the 1D mass fractions. And in the 3D simulations, we multiply it with the 3D value from the transport equations. And in this way, some influence of cross diffusion can still be taken into account, and we get an even more accurate solution for, especially for CO. Now, a couple of words about the lookup table. So when you have an equidistant table, a lookup is very easy, but large tables are necessary. With unstructured tables, you can have local measure refinements to accurately capture local extrema. So we need some efficient methods to find out in which cell in the table our query point is. A very simple but still computationally efficient method is by subdividing the 2D domain into vertical slabs and keep a sorted list of all the edges in the slab. This is basically this basically means doing two binary searches, so the computational time is of the order of log n. However, the memory requirements can, in the worst case, still be of the order n squared. A better method with a lower memory requirement is the trapezoidal map approach. And in this approach, every node divides the cell above and below it with a vertical line, let's say, creating new intermediate nodes and vertical line segments. And such data can be stored in what's called directed acyclic graphs that allow easy traversal through the data. And the big advantage of these trapezoidal map approaches is that the memory requirements is now only of the order n, because every node only introduces 2 new nodes and 4 new edges. Now, if we want to model hydrogen, then we need to do a little bit more effort, because hydrogen burns a little bit differently compared to methane flames. So a very important physical phenomenon that needs to be modeled is preferential diffusion. So a sketch of what this is. So basically fuel to air ratio or equivalence ratio in a purely premixed gas is constant. So in this example, I have purely premixed hydrogen and air coming into this domain. So the equivalence ratio, let's say, is constant in the entire domain, you would say. But in hydrogen flames, hydrogen diffuses out of the flame region with positive curvature towards regions of negative curvature, so towards the flame base. Now this means that the flame tip will have locally a leaner mixture, and the flame base will locally have a richer mixture. And premixed hydrogen flames therefore often have these open flame tips. This behavior influences, of course, the burner temperatures and also emissions. Now in the images here on the right, we see from left to right some hydrogen flames with a decreasing equivalence ratio. Each time that we decrease the equivalence ratio, the inlet velocity is adjusted again to the theoretical value for the laminar flame speed at the inlet, such that the flame height stays more or less the same. And what we then see is that for lower equivalence ratios, also the flame tip opening becomes stronger than for high equivalence ratios. And on average, the heat release rate is closer to the burner surface. So this has a large impact on the burner temperatures, which can then in turn also influence thermal stresses and flashback behavior. So this is definitely something that you have to take into account in hydrogen modeling.
Nijso, one question. That basically means that the further along the domain you go, your flame becomes too lean at some point to burn. Is that then the reason why you have an open flame?
Yes. So let's go to this first picture. So here at the inlet, we have, let's say, purely premixed hydrogen and air with a certain equivalence ratio or a certain lambda value.
Mhm.
But this hydrogen moves, diffuses, and that means that here in this flame tip, the equivalence ratio is very low, or let's say the lambda is very high.
Mhm.
And this is why it does not burn here. So there is actually almost no hydrogen here in the flame tip.
Yeah, so outside of flammability limits locally.
Yeah,
basically.
exactly.
No. Okay, thanks.
Yeah. Yeah, so how is this preferential diffusion modeled? Well, Fick's law of diffusion is often used to describe the mixing and diffusion of two species which holds in a binary mixture, and when the molecular weights of the species are the same. Fick's law also tells us that species diffuse into regions of lower concentrations and that the diffusion is faster when the gradient is larger. Now, with multiple species, however, one can derive from kinetic theory a coupled linear system of equations. And an already simplified system is given here by the Stefan Maxwell equations. And the first order approximation is then given by the Curtis-Hirschfelder approximation, leading to an expression similar to Fick's law for multi-component mixtures. Now, the diffusion term in the Curtis-Hirschfelder approximation is not an actual binary diffusion coefficient, but some kind of a bulk diffusion coefficient describing the diffusion of species, let's say K, into the rest of the mixture. Now, how do we deal with this in practice? So we simply compute all this information in the 1D detailed chemistry simulations as well, and we also tabulate it. So this is just an illustration to show that. So the left half of each of the image shows the Curtis-Hirschfelder approximation, and the right half shows the complete multi-component diffusion model. And it turns out that, at least for this hydrogen flame, the, let's say, Curtis-Hirschfelder approximation is a sufficient approximation of the diffusion process. Now these detailed simulations show that due to preferential diffusion, the fuel-to-air ratio does not stay constant in a hydrogen flame. So this is a contour plot of the mixture fraction, where a normalized quantity Z is 0 in a pure air stream and Z is 1 in a pure fuel stream. And I will skip a little bit. I will go through this a little bit faster. So in the end, what we need to do is we need to solve next to the progress variable and enthalpy equation, the mixture fraction equation. And if we have preferential diffusion, then we have a couple of additional preferential diffusion terms that occur. And these additional terms we can also tabulate. We store it in the lookup table. Now, for purely premixed flames where preferential diffusion can be neglected, the flame can be described using the progress variable and the enthalpy. But for flames where the mixture fraction does not stay constant, we need then to solve this additional transport equation for the mixture fraction. Now the lookup tables are again obtained by solving 1D flames for different enthalpy levels. But in addition, we also have to vary the equivalence ratio and compute the mixture fraction. This leads to the black manifolds shown in the figure, where on each of the manifolds the equivalence ratio is constant. And then we map these 3D manifolds back onto a series of planes with constant mixture fraction. And that leads to a, let's say, quasi-unstructured lookup table. So this means that our 3D approach is basically a collection of 2D tables at different constant mixture fraction levels. So in this quasi 3D lookup, we want to retrieve a quantity that's at a certain point in the progress variable space, and we therefore find the two mixture fraction levels that enclose the query point. We find the 2D faces that contain the predicted query point. Then we do a 2D interpolation twice for the mixture fraction level stored in lookup table. And after that, we linearly interpolate along the mixture fraction direction. So we try to make this entire workflow as smooth as possible, and a number of tools were developed for this. So we have automatic MATLAB and Python scripts that were created to be able to generate the 1D solutions with different chemistry solvers. Then we have created a graphical user interface. It was developed with TU Aachen and Bosch RTC Sunnyvale to create and analyze 2D and 3D lookup tables, including analysis of the optimal progress variable. And we are also looking into open sourcing this, so hopefully very soon you can all use this. And the flamelet approach to simulate methane and hydrogen flames was implemented in the open source CFD solver suite SU2. And the 2D lookup table implementation is already available for the general public. Now, I would like to go into the very interesting topic of adjoint design optimization. So now we have all these simulation tools available. We would like to use these tools to analyze and optimize combustion appliances. So what options do we have available? So suppose that we have a design with two design variables that are allowed to change. So this can be a width or a radius, some geometric parameter. And we want to find the optimum design, say a design with the highest heat transfer or the lowest pressure drop or the lowest emissions. And this particular design has one global optimum, and we want to find it. So how can we do this? Now, we can, of course, simply do 200 simulations, map the entire design space. And if the optimum is inside this range, then we have found the optimum. This is, however, very costly. So a better way is to use gradient-based approximation. So what do we do then? We start with an initial design, and then we vary the first design. We vary the design first in one design variable, and then in another. We perform a CFD simulation for both. And for both simulations, we get a gradient that tells us how the objective changes as a function of the design variable. And then we change the design in the direction that gets us closest to the optimum. And we continue until we reach the optimum. This is still a very expensive procedure, especially when you have many design variables. In this case, there were only two. Now, if only there was a method that would give us the sensitivities and the gradients for the search direction that does not require multiple CFD simulations. And this method exists, and it is called the adjoint method. The adjoint method gives you the gradients that you need to move towards the optimum, and its computational cost is independent of the number of design variables. It does depend, however, on the number of objectives, but usually the number of objectives is much lower than the number of design variables, rarely more than 3 actually. So how does this look like? I will just sketch it, not give you too many equations. So I will discuss this 2D burner and heat exchanger. The flow is from left to right. We have a mixture of methane and air in this case, or fuel and air in general, which enter the domain. The flame is stabilized on the burner. There is a heat exchanger placed downstream of the flame. It extracts heat from the combustion products. The combustion products cool down, and the thermal efficiency at the outlet is determined from the amount of heat that could be extracted by the heat exchanger And the primary function of the heat exchanger is, of course, to extract heat as much as possible from the hot gases. But we also want to have, of course, very low CO and NO emissions. So let's say we want to minimize NO. Our objective function J is the mole fraction of NOx at the outlet. And to achieve our objective, we can modify a set of control variables, also called design variables. In our case, these are the surface nodes of the heat exchanger, specifically the X and Y coordinates of each of the surface nodes. And if we now move one node by a distance delta X, and we recompute the CFD solution, then we get a new value for our objective function J and the NOx concentration at the outlet, which is the NOx concentration at the outlet. So we can therefore compute the gradient dj dx and the change in objective function with respect to a change in the design, which is the change in objective function with respect to a change in the design variables. So we want to minimize J. And since we want to minimize this, we can then determine in which direction we actually need to move the surface node after this procedure. And we can then do this for each of the surface nodes. It does mean, however, that our governing flow equations, and this means the system of partial differential equations that we call R, depends not only on the flow variables W, the mesh coordinates X, but also on the control variables alpha. So how does this work in a little bit more detail? So it uses the method of Lagrange multipliers. So what you do then is you construct a Lagrangian function that contains the objective J and this unknown, or let's say arbitrary Lagrange multiplier. And then after some nice manipulation that is an exercise to the reader, we end up with this beautiful expression. And all these terms can be obtained from one or multiple Navier-Stokes solutions. And we can compute basically the sensitivities. However, this expression contains here a very nice term, which is the change of the Navier-Stokes solution with respect to the change in design variables. And this is super expensive. This basically means that we need the Navier-Stokes solution for each of the design variables. So if all surface nodes of this heat exchanger are a design variable, we could have 100 points, so 200 design variables. That means that to get this term, we need to solve 200 times the Navier-Stokes equations. And that is expensive. However, it is pre-multiplied by this term here, containing this arbitrary Lagrange multiplier. So what we can do is we can simply solve this equation for the Lagrange multiplier, such that this equation is 0 and then this entire term drops out. And this equation is called the adjoint equation. Just to go back, so the adjoint equation, it's just a system of linear PDEs that you can solve for approximately the same cost as a single CFD simulation. So it's much cheaper to solve this equation and let this entire term drop out than to solve actually this term. Now in practice, we do not move the mesh nodes directly, but instead we use freeform deformation boxes to deform the mesh. The sensitivities are then projected onto a freeform deformation box, and the nodes of the FFD box are moved. The mesh, or in this case the TU Eindhoven logo, smoothly deforms with the FFD box deformation. And this results in a much smoother deformation of the surface than when deforming the mesh directly. However, we still have to be careful because also the FFD box approach can lead to invalid meshes or deteriorating mesh quality, which will prevent convergence on the deformed mesh. So what is the entire workflow that we use? We compute the primal solution. Then we compute these adjoint equations. Then we compute the surface sensitivities from that. We deform the mesh. If the mesh is actually bad, then we can still do use a meshing tool to improve the mesh quality, for instance, the pointwise remeasure. And we do this entire loop again and again until we are satisfied with our objectives. So the results of an actual adjoint optimization. In this case, we want to optimize this burner and heat exchanger configuration using laminar, purely premixed methane air flame. So in that case, we also have CO to minimize. The table at left shows the objectives that we want to minimize, and here the weight functions that we have used. So they will tell us how much more important one objective is compared to another. And what we do is we normalize all mean outlet values for the original geometry to 100. So temperature, CO, and NO in the baseline geometry is 100. We see that the flame is also very close to the heat exchanger here, leading to especially very high CO at the outlet, because CO does not have time to react to CO2. And NO starts to form almost as soon as the temperature rises in the reaction zone. So NO is formed only in this small hot zones here, but then quickly stops being produced inside the heat exchanger. So NO is already relatively low in the baseline case. Now, if we optimize purely on temperature, what happens is that the heat exchanger basically increases its surface area, and the outlet temperature can be reduced by around 10%. You see that here. But at the cost of a slightly higher CO, NO stays almost the same. Now, if we optimize purely on CO, what happens then is that the heat exchanger opens up downstream of the flame tip to delay the cooling of the combustion products. CO can in that way be reduced by almost 50%. This, however, at the expense of a higher outlet temperature and a slightly higher NO. If we now optimize for NO only, we see that the heat exchanger moves a bit towards the flame in order to cool the hot zones at the sides of the flame, and the NO can be reduced by approximately 20%, but at the expense of mainly CO, which increases by 90%. Now, if we optimize CO and NO together, and then we get a very thin heat exchanger, almost a sliver. Obviously, the temperature will be affected tremendously by this. So for this combination of weight factors that we have used, CO is reduced by 70%. NO is reduced by 20%, but at the expense of temperature, which is now 80% higher than the original geometry. Now, if we optimize all three objectives together, we see that we can still reduce CO and NO without deteriorating the temperature. Now, these results depend on the choice of weight factors, of course, but this illustrates that it is possible to optimize all three objectives at the same time. So here we see the heat exchanger geometries next to each other. The shape change for all these optimizations is quite large, and it is clear that manufacturability might be an issue, especially for the multi-objective optimized geometries. And this is actually part of ongoing research. To conclude, we can optimize combustion appliances. We have developed tabulated chemistry models for hydrogen, which have been implemented and tested in the issue 2 code. We can optimize for certain objectives, but there are certainly also many challenges left. For instance, thermoacoustic noise is an interesting problem. We would like to minimize the noise, or actually the gain of the flame transfer function, which determines if a disturbance gets amplified or not. Optimize the mass flow distribution on this burner. In this example, you see that we do not really have a very homogeneous flame pattern. Which leads to hotter and colder zones and high thermal stresses. We will, of course, want to keep these thermal stresses low, so we can also minimize. We can also look at thermal stress minimization in the framework of a joint optimization. Now, if we inject fuel into the airstream, we might get vortex shedding, which causes instabilities in the flow and can also produce noise. This is also something that we want to avoid, of course. So many challenges we are still working on, many challenges still lie ahead of us. And I hope that with this presentation, I have shown you a little bit of insights, and also that a joint-based optimization for combustion is a very useful tool, and that there are many challenges that are just waiting to be solved in future projects. So thank you very much for your attention. If you have any questions, you can answer them. I can answer them now or in the near future for you.
Thank you very much. Do you hear me now?
Yes.
Yes.
Ah, fantastic. Yeah. Because it's really nice to see Nijso's approach combining so many aspects of his career. And so maybe the introductory question could be, I hear you talking about adjoint methods for decades, let's say. How did you get interested in adjoint methods?
That's now I have to think back. Yeah, so I think it started. So of course, at a certain point, you hear that this method exists, and I think this started with a visit to Stanford, where I visited the group of Juan Alonso. So that's the former group of Anthony Jameson. And Anthony Jameson was basically the pioneer of, well, of many things, but also of this adjoint method. So there was a strong research, a lot of research done in that group. So it actually started with this visit, and then with a collaboration with Stanford, and in the end we actually had a PhD student from the group who just finished, and we convinced him to work for a while at our Bosch location close to Stanford in Palo Alto. And yeah, that's actually how it started.
So it was really in the beginning of your career in Bosch.
Yes, exactly. So
okay. Thank you. No,
yeah.
Other people have other questions probably.
I have one question. Nijso, you mentioned the weighting parameters. How do you choose them? Is it just like based on experience, or is there like some more systematic approach for that?
Yeah, so it is a bit of both. Yeah? So one thing that you can observe is that if you look at the actual, let's say, value of temperature, we are talking about, let's say, the order of 1000 Kelvin, so 10 to the power 3. But if we look at CO, mass fractions of CO, then we talk about 10 to the power minus 3. So in terms of values that we are looking at, there's a factor of 10 to the power 6 difference between these quantities. So what we see is that these weight factors initially have to be chosen in